Hello, welcome you all. In this video session, we will derive the stiffness matrix for the convection problem. In the last video session, we have derived the stiffness matrix of the element for the conduction problem, that is K is equal to AK by L and 1 minus 1 minus 1 1, where A is the area of the element, K is the thermal conductivity of the element, and L is the length of the element. Now we will derive the stiffness matrix for the convection. Convection means it is one of the mode of heat transfer from the material to the surrounding. Okay, in this element, okay, where one end it is fixed or it is maintained with a temperature or specified temperature T1, and at the other end there is a convection mode of heat transfer from the material to the surrounding, where the material temperature is T2 and the atmospheric temperature it is T infinity, where T infinity it is the atmospheric temperature. So the element which has two nodes, node 1 it is maintained with the temperature T1 and node 2 it is T2, and the atmospheric temperature it is T infinity. Okay, we already know that to derive the stiffness matrix we need the strain energy. By the strain energy, if the nodal temperatures are removed, then it is the stiffness matrix. Okay, this is the stiffness matrix derived from the strain energy, where this H it is the material property for the convection, that is the heat transfer coefficient, and N it is the shape functions, transpose of shape functions, N it is the shape function, and D is the elemental area. Okay, we already derived in the earlier sessions the N1 and N2 values. N1 it is x2 minus x by LE, and N2 is equal to x minus x1 by LE. Okay, now the heat transfer, the convection heat transfer taking place at the node 2. Okay, let us substitute the value of node 2, where x value is x2. Okay, substituting x is equal to x2 minus x2 divided by length of the element. X2 minus x2 it is 0, so n1 is 0, and x2, substituting x is equal to x2 here, x2 minus x1 it is nothing but length of the element. LE get cancelled, so it is 1, so it is 0 and it is 1. So this shape function matrix it is 0 1, shape function matrix 0 1, and the transpose of this matrix it is 0 1. Okay, substituting this value here in this equation, where H is the heat transfer coefficient, here it is the transpose of the matrix 0 1, it is a column matrix, 0 1 it is the row matrix, into dA. Okay, so simplifying this, we have the stiffness matrix H equal to, okay, product of these two matrix it is 2 by 2 size matrix 0 0 0 1 integration of 0. Okay, this is the stiffness matrix for the convection. Okay, when you are using this expression for the stiffness matrix for the convection problem, make sure that always the convection heat transfer taking place at the node 2. Okay, if it is taking place at the node 1, then the matrix, you have to change the matrix into 1 0 0 0. Okay, if it is 0 0 0 1, if 1 here in the A22 position, then the convection heat transfer is at the node 2. If this one it is at the node 1, or if then it is A11 position, then the heat transfer is at the node 1. Okay, this is the convection stiffness matrix for the convection. Okay, as it is a element and there is obviously conductivity is there, so conduction plus convection, that is the total heat transfer stiffness matrix. Already we have the conduction stiffness matrix AK by LE 1 minus 1 minus 1 1, and this is the convection heat transfer stiffness matrix HA 0 0 0 1. If 1 is at A22 position, then it is at the node 2. If heat transfer, convection heat transfer, it is node 1, then you place this one at the A11 position. Okay, this is the total stiffness matrix considering conduction and convection. force vector due to free end convection. In order to find the nodal temperature, we need to have force vector and the stiffness matrix. F kq is equal to F. K is the stiffness matrix, Q is the nodal temperature matrix, and F is the force vector. Okay, to find the nodal temperatures, that is 2T matrix, we need to find K and F, where K is the stiffness matrix. Already we have derived the stiffness matrix considering conduction and the convection. And force vector, this is the force vector considering the convection. Okay, AH T infinity N1 N2, N1 and N2 values are substituted here, so it is 0 1. Okay, this is also similar. If heat transfer, if the convection heat transfer at the node 2, then you have to write 0 1. If the convection heat transfer at the node 1, then it is 1 0. Okay, now to find the nodal temperature, this equilibrium equation can be considered, where K is the stiffness matrix, T is the nodal temperatures, that is T1 T2, and F is the force vector. This is the force vector considering the convection heat transfer. Okay, thank you.